Okay. Hi, everyone. Thanks for having me here. I'm very glad to be here with you today. I'm Mateusz Jurczyk. I work on low-level offensive security at Google Project Zero. And today I will be talking about the practical exploitation of some registry vulnerabilities that I have found in the last few months in the Windows kernel. So let's get started. First of all, just a very quick recap of what the registry is. It's basically a database in Windows for storing settings for system and applications. The three essential concepts are hives, which are like pieces of this database that are backed by files. Then inside of them you have keys, which have names, security descriptors. You can open handles to them and stuff like that. And inside of them you have values which actually store the data that you want to put in the registry. By default in Windows you have at least two tools for management by administrators and power users, such as the graphical regedit and the command line reg.exe. You also get a very well documented registry API for when you are a software developer and can actually want to use the registry. And what is important from the security perspective is that most of the implementation of the registry is in the kernel. So many of you may be familiar with this view. This is the standard registry editor, and you can see here on the left the structure of the registry, the top-level keys, and the tree structure underneath it with the key names. And on the right, you can see the values with different kind of types and data assigned to them. So that's basically what the registry looks like, more or less, to most users at least. When it comes to the history of the registry, it was first introduced in Windows 3.1, so very long time ago. It was to replace ini files as the means for storing configuration data. Current both code and design is very deeply rooted in Windows NT 3.1 and Windows NT 4, so that's also around 30 years of history of the Windows registry. First of all, it was a very, very simple interface. And then over the next 30 years, even though it may not be very obvious from the graphical interface perspective, really a lot of improvements and extensions have been added, most related to performance, first of all, because Windows registry is very central to the operating system and to its performance. So some optimizations have been implemented there, and there were some backwards compatibility mechanisms and also some new features, such as support for values that are longer than 1 megabyte, registry callbacks that can be used by antivirus, for example, and EDRs, transactions, application hives, differencing hives, and so on. So quite a few interesting features there. And since Windows Vista, it was possible to load fully controlled binary hives by normal users without having any special privileges. So that actually extended the attack surface a lot by allowing us to load these controlled hives without any special rights in the system. Here on this diagram, you can basically see the progression of the size of the code base. I basically decompiled every major version of Windows NT kernel and figure out which functions are responsible for handling the registry and counted the number of lines of code. So the main takeaway here is that it started at around 10,000 lines of code in Windows NT 3.1, and over the next 30 years, it has grown basically tenfold to around 100,000 lines of decompiled code in Windows 11. So it's really been increasing in size. When it comes to the registry as an attack surface, I wanted to talk about the good and the bad parts. So when it comes to the good parts, first of all, as I mentioned, is basically kernel code that is reachable from many unprivileged contexts. So we can get LPE if we find some interesting vulnerability in the Windows registry. It also processes very sensitive data, such as system configuration and user credentials. So even if we get some bug like an information disclosure, that can also have a very big security impact. The registry itself also has some very interesting parts of the design, which make it a little bit error-prone. So it's self-healing, it's size-bound, and it's very heavily optimized. It's also a very interesting mixture of complex C code that is basically was written in different eras of Microsoft and in general software development practices. So we have literally code from 30 years ago directly interacting with code that was written, for example, 1 month ago, which also makes it a very interesting target. And finally, there are a lot of potential bug classes and attack vectors that you can target through the registry. And as for the bad parts, first of all, there is, of course, an asterisk because you can consider it bad or good. But basically, first of all, the registry I found is very hard to fuzz effectively without investing a lot of time into actually writing something that is registry specific. We don't have access, obviously, to the source code, and even though documentation exists for some parts of the registry, it's basically non-existent for some other areas as well. We get access to public symbols that Microsoft makes available for the Windows kernel, which gives us function names and some structure definitions, but also not all of them. So we have to do quite a bit of reverse engineering. And that means that we have to invest a lot of time and energy to actually, first of all, reverse engineer the code and then understand the logic and what it actually is trying to achieve. And as with every research, here's the same. Not all bugs are good. There are better and worse bugs. When it comes to this effort, it all started, well, actually two years ago now, as a Hive fuzzing project. So I didn't intend to do this whole auditing research, but I was just developing a kernel code coverage-based fuzzer, and I just wanted to use registry hives as one of the targets for fuzzing it. And I managed to find one bug through simple bit flipping, which was nice. And I started doing root cause analysis to see what exactly was it about. And I found, first of all, that registry is really not that great for fuzzing. But also I found that there is a lot of code that is very interesting, and it could be good to, instead of doing fuzzing, just manually audit all of it. And you know, I got so hooked up that it lasted for 20 months of basically just looking at this code. So the results are that I filed 39 issues in the Project Zero Bug Tracker because they had some significant security impact. I also reported 20 issues outside of the tracker because they had either low or unclear severity, but I still wanted Microsoft to know about them. And overall, it was 50 CVEs that were assigned to Microsoft across 15 different monthly bulletins. And there were really a broad range of everything in these bug reports. So if you're interested in learning more about the specific bugs, you can just go to the Project Zero Bug Tracker, and all of the bug reports are now derestricted, so you can read the descriptions. Every bug also has a proof of concept, so we can immediately start experimenting with those bugs if you want to. I also put the reports for the low or unclear severity issues on the Project Zero GitHub as well, so you can check that out. And also I have started to publish some blog posts on our blog regarding this research and also some general registry internals, and that will continue in the next few weeks. But basically the topic of this talk is about specifically exploitation and the offensive angle of the registry. So let's start with thinking about which bugs can we even start to think about using for LPE. And there are three main groups that we could use here. First of all, we have logic issues in the registry, which in general are pretty good for exploitation, but I haven't found that many of them. I have found some, but it may have something to do with the fact that James Forshaw from my team has looked at the registry before looking for logic bugs, so there wasn't too much left to be found there. We also have pool-based memory corruption that was quite prevalent, that obviously can lead to local privilege escalation, but it basically boils down to exploiting the Windows kernel pool, which I don't find as novel as I would like to. So the third and I think the most interesting part of this is the Hive-based memory corruption, which is basically a new unexplored class of issues that is specific to the registry, and that is quite fun to exploit. So when I say Hive-based memory corruption, what exactly do I mean by that? So let's start by saying that hives are basically encoded in the regf format, which is a binary format, proprietary, but quite well reverse engineered. It has several versions, but all of them are pretty much very similar and backwards compatible. And when a hive is loaded in Windows, what happens is that the system basically directly maps the file as it is on disk to memory. Technically, it's typically achieved by having a file-backed section inside of the special registry process, which is a helper process. And so we have these file-backed sections in the user space of this process that you can find in Task Manager, for example. And then both the in-memory and on-disk copies are continuously synchronized by the operating system. So if we perform some operation in the registry, some data is written to the memory mapping, then it's flashed to disk very soon by the operating system. And the Hive-level structure of the registry is quite simple. So we have a 4 kilobyte header, which is called the base block. That is followed by one or more 4 kilobyte aligned bins, which also have their own headers. And the rest of the bins is basically filled with cells, which are chunks of data with arbitrary size, and they can be either marked as allocated or free. Here is an image from the Great Windows Internals book, which explains this, and we can see all of the parts here. The base block, then a bin, the first bin that is completely empty, meaning it probably has a single cell that is free and has 4 kilobytes. And then in the second bin, we actually have some cells that are allocated and store the data of the registry and the registry tree and all of the information contained within. What we really want to focus here are the cells. So the headers are not really that important. Everything that is interesting is in the cells. Depending on how you count, there are around 8 to 10 different types of cells, which corresponds to keys, values, security descriptors, list of subkeys, and so on and so forth. And these structures are part of the symbols that Microsoft makes available. So they are actually well documented, and you can check them out in IDA Pro, for example. Also one important part is that these cells have to reference each other in the Hive, and this is achieved by something called cell indexes, which are basically 32-bit offsets within the Hive that specify the offset of another cell that is being referenced. So here we have a very basic example of some keynode, which is the most basic structure. In the registry on the left, you can see the structured prototype dumped in Windbag, and on the right, you can see some actual data corresponding to it. Most of it, as you can see, is either all zeros or all ones, but there are a few interesting non-zero parts. So first of all, we have the signature equal to 2 bytes NK, which just means that it's a keynode. Then we have the flags of the key. We have the timestamp. We can see that this key has 2 subkeys, and there is a cell index to the subkey list. It has also a cell index to the security descriptor, and it has a name of root because this is a dump of a root key inside of a Hive. And here, highlighted in orange, you can also see specifically the cell indexes that are contained within this structure. So we have the pointer to the parent. It's all ones because this is the root key. And then most other cell indexes are also just FFFFFFF, which means that it's not pointing anywhere, but the two actual cell indexes that point somewhere are to the subkey list and to the security descriptor, which always has to be assigned to a key. And then here you can see a diagram of the relationships between cells. It's not really that much important here, but basically every cell index has to point to a specific type of object. So we start with the keynode, which is the most important part, and that has cell indexes to the security descriptors, to the subkey list, and to the value list that then references specific values, which then reference the backing buffers behind these values. And when it comes to the state consistency guarantees, what happens is that every time you load a Hive in the operating system, before it is actually loaded, the kernel goes through all data inside of the Hive and tries to verify the overall correctness of it. Whenever it finds some weird data that seems inconsistent or wrong, then the kernel tries to fix it. For example, if there's some flag that shouldn't be set, it just clears it and tries to continue with the process as much as it can to load the Hive. And if something is broken beyond repair, then the kernel just, for example, deletes the whole key and still continues to load the Hive. So it does everything it can to load the Hive successfully, even if it has to slash some things off completely. So the correctness of the mapping of the Hive internally is guaranteed on load, and also at runtime, if you perform any operations on the registry, the kernel also has to keep the Hive structure internally consistent at all times. And this is really a security critical invariant. So if you are able to break this invariant and create some weird inconsistent state inside of the Hive mapping, you may get very interesting side effects, as we will see soon. So now the question is, how would we even corrupt the Hive? And the answer is very simple. Cells are chunks of binary data, and they are parsed and handled in C. So obviously, you can have bugs there, as every C software has. Some examples specific to the registry is that security descriptors are reference counted. So if something goes wrong with the reference counting, you can get a cell that gets freed, even though it shouldn't be freed, and you get a use after free. Similarly, if you have some dangling cell index pointing somewhere to some cell that gets freed, even though it shouldn't, you get also a UAF. You can have situations where you have an unchecked cell index because during loading of the Hive, the kernel actually forgets to check some specific cell index, and then you get an arbitrary read and write inside of the Hive because you can get it to point anywhere inside of the Hive. You have variable sized arrays, which are always a problem in C, which can lead to buffer overflows, and any other inconsistencies. For example, you have a size member somewhere that is too big, then you get out-of-bounds accesses. So you can actually get all of the standard, typical C low-level memory corruption inside of the Hive data. And so I wanted to show you one example of such a bug. This was actually the first bug that I manually found in the registry. And so we have this function called CMP check and fix security cells ref count, which is very self-explanatory, right? It is executed when the Hive is loaded in the system, and it goes through all of the security descriptors and checks if the reference counter that was loaded from disk for the security descriptor is not smaller than the actual real number of references from keynotes to that security descriptor. And if it's smaller, then it gets adjusted to be consistent with the actual number of references. So this obviously seems correct, but the problem is with the fact that it only fixes inadequately small reference counters and not bigger ones. So here we have an example of a security descriptor which has 3 keynotes that are pointing to it, but when it gets loaded from disk, the reference count is equal to 2. So this function executes, it sees that the reference count is wrong, and it fixes it, adjusts it to 3 so that it's consistent again, and everything is fine. But of course, the problem is when you set it on disk to FFFFFFFF, then this function thought everything was correct because of the operation in the if statement. So it goes through, and we get this huge reference count. And because of the fact that we have no integer overflow checks, when incrementing this reference count, when you add another key that uses the security descriptor, it overflows to 0. When you get another key, it goes to 1. And then when you remove a key, it goes back to 0. The kernel thinks that it should be freed. And so the cell is freed, but we still have 4 dangling references to this cell internally in the Hive. So this is one very simple example of a memory corruption in the Hive mapping. This is, to be honest, this is a great bug because we controlled everything here. We control when the UAF gets triggered and so on. In total, in my research, I found about 15 bugs that were kind of equivalent in terms of the primitive, meaning that they resulted in some kind of Hive memory corruption. And so we'll be basically exploiting this kind of bug in this presentation. And so I structured this talk a little bit like a chess game. So let's start with the opening and thinking about the Hive allocator and how it works exactly. So we have 3 functions internally in the Windows kernel responsible for allocating memory in the Hive, meaning allocating cells. So it's kind of allocating memory, but also data in a file, because it's the same thing in the registry. So we have the allocate cell function, the reallocate, and the 3 functions that you would typically expect of an allocator interface. It's not really important how exactly these function definitions look like. Then if you go to IDA, you can see the references to these functions, which is kind of interesting to see exactly when these operations are used for which types of high-level registry operations. And also, it was a great starting point for me to see these references and treat them as a starting point for actually looking for some interesting bugs. And so in terms of the security, the allocator is really not great in terms of security mitigations. So we are all used probably to having heap cookies and different kinds of double free detection and stuff like that. None of that is found in the Hive allocator. It's also fully deterministic, meaning that allocations always land exactly in the same place. If you are using application hives, which are hives that are private to one application and other applications cannot access it, then we also don't have any external noise generated by the environment, which makes it basically 100% reliable what happens inside of the hive. And all of this means that all of the Hive state grooming that we need to do can be performed basically with a single documented registry function called regSetValueX, which just creates a value and the backing buffer for that value that we can use to store some controlled data. Here is an example from taking the previous use after free on the security descriptor. So we have an example Hive, and there is a freed cell with 4 other cells still pointing into that cell. It's freed now, and basically it's super simple to reclaim this spot in the Hive space by using a single API call. This is the main takeaway from all of this. So, okay, now let's go to the middle game and thinking about how we can make the Hive corruption somehow useful for us. Because the current capability that we have right now with the bug is that we have a locally running exploit Through going through the kernel address space, calling into system calls, we can load our own hive called exploit.dat, and we can cause some kind of corruption inside of this hive. This is what we have right now. But just having this isn't particularly useful if we are just corrupting our own hive, because first of all, since it's our own hive, we control the file. There aren't any secrets that we could steal from this hive using some kind of info leak. Furthermore, there is also no trusted data that some other process would trust and that we could modify to get some interesting side effect. And lastly, there are also no virtual address space pointers inside of the hive that would allow us to kind of escalate from corrupting the hive into corrupting something else in the operating system, because of the fact that the hive data is always self-contained, and the only kind of references that you have is the cell indexes, which also point back into the same hive. So the first step what we have to think about is finding a way to corrupt some other kind of memory in the system, such as some kernel pools or some other type of trusted memory. And when I started thinking about it, I thought about a few potential options that you could take, and all of them are kind of viable, but they have some different drawbacks. So first of all, one idea would be to, okay, if it doesn't really make sense to corrupt our own hive that we load, why don't we just run an exploit in the context of some system hive that is trusted and has this interesting data that we could corrupt or leak. So, for example, execute the exploit in the context of the software hive. And sure, it is possible, but the problem is that in order to be able to run an exploit directly in a system hive, you really have to have a very good bug that allows you to cause some memory corruption without having binary control over the file, because you don't have write access to the software hive file, right? So it requires a really good bug that is triggerable only via the standard APIs or standard operations, such as creating and deleting keys and so on. And such bugs do exist, so I found like 2 or 3 of them in my research, but they are not very common because they are really good bugs. They don't have any prerequisites. So this technique is possible, but it wouldn't be really universal. Another idea would be to take advantage of the fact that in the user space of the registry process, you have mappings of different hives mapped basically next to each other without any gaps in between. So you can load your own hive and you can then corrupt it and use a linear buffer overflow to cross the boundary between your own hive mapping and the hive mapping of some different trusted hive in the system, and basically corrupt the software hive or some other trusted hive this way, which also is viable, I would say, but here the disadvantage is that we are kind of reliant on the specific memory layout of these mappings, which is also not ideal, because it's hard to predict exactly how these mappings are going to work on a running system that we don't fully control. The third idea could be that we try to basically corrupt page pool memory, and how it works is that even though most of the hive data is mapped in the user space of the registry process, there are some exceptions to that, and in some cases the mappings are actually residing in the kernel address space and the kernel pools. So these exceptions are the system hive, which is always in the kernel pools. You have the hives that didn't exist before, and you freshly create them with a call to load the hive, and the kernel just creates the hive from scratch. Then it's also loaded in the kernel pools. And also you have the volatile space of a hive. So every hive has a stable space and a volatile space. The stable one is the one that is backed by a file, and the volatile one is the one that is only backed by memory, and it will just vanish on the next system reboot. So the volatile space is also residing in a kernel address space as a normal page pool allocation. So you can in this case corrupt the stable space of a registry hive. From there you can elevate into corrupting some data in the volatile space, and there you can again cause some kind of linear buffer overflow to corrupt some adjacent data allocated from the page pool memory, which is also a very good idea. I would probably use this one for exploitation if I didn't have anything better. But again, it boils down to exploiting a pool memory corruption, which I really didn't want to have to do. And then the fourth idea would be to corrupt the registry cache structures, because in Windows, you have the mapping of the Hive, but also the system doesn't really want to do all of the context switches to read data from the Hive, from the registry process, if it doesn't really have to. So a lot of the data from registry Hives is also cached in some kernel address space structures. For example, you have structures such as KCBs, which translate to key control blocks, and they have some of the same data that is stored in the Hive mapping. So if you corrupt the Hive mapping and you create some inconsistency between the Hive and the cache in the kernel pools, that you can also trigger some kinds of use after freeze and other memory corruption. But again, this boils down to page spool memory corruption. What we would ideally be aiming for is something like this, where we just corrupt the exploit.dat-hive mapping, and from there we get arbitrary read and write, which is, of course, the dream of all of us. Turns out that this can actually be achieved, and the trick is, again, to use the cell indexes. So as I said before, cell indexes are 32-bit integers that are used to cross-reference cells within the same Hive. In the file, they have a very simple meaning. They are just offsets, but at runtime, it's a little bit more complicated because of the fact that in memory, the Hive mappings are not just one giant mapping of the whole file. You actually map these Hives on a bin granularity, so that's what the bins are for, in order to have a little bit smaller chunks of these mappings. And that is motivated by the fact that registry Hives can grow and shrink dynamically, so you want to have some room to make those allocations and free them. And because of this, we cannot just use a simple addition to translate the cell index into the corresponding virtual address. Instead, there is a page table-like structure that is called a cell map that is used to perform this translation. So this is another image from the Windows internals books, and you can really see that it's very similar to what you would how you would normally imagine the x86 page table, for example. But here we have two layers: the directory and the table. And then once you translate these two layers, you have a byte offset of 12 bits that you add to the final address, and you get the address that the cell index translates to. So this is a simplified pseudocode of the HVP get cell paged internal kernel function, which is the function that is used for performing this kind of translation. And it basically looks like how you would imagine it to look. So we have some bitwise operations to extract the specific parts of the cell index, and they are used to dereference the specific parts of the cell map. And at the end, we just return the final result of this computation. And then the typical usage of this cell index is as follows. So we have this hypothetical function called CMP set value data, which imagine it's used for setting the data of a value that we specify through the pointers. And we basically have three steps here. So first of all, we have the value node, and we have the cell index of the backing buffer in the data member. So what we want to do is we want to translate the cell index into the virtual address of the backing buffer in the first step. Then we basically perform a normal memcopy to copy the data from the buffer into the Hive mapping. And then as a third step, it's not really that important. We just call a release function to let the operating system know that we are no longer using this cell. And so what we want to do is we want to abuse these cell indexes. So of course, normally the cell indexes are within the bounds of the Hive size. But the natural question is, if we can set the cell index to an arbitrary 32-bit number, what happens if we set it to a value that is greater than the Hive size? And the answer is very simple. The kernel doesn't care. The kernel always assumes that the state of the Hive is consistent internally, so the cell indexes are trusted. And the Hive, the HVP get cell page function just performs the usual cell walk, regardless of whether the cell index is valid or not. However, the problem is that every level of the table is normally allocated in full size, and it's zeroed out after allocation, which means that probably if we try to use an out-of-bounds cell index, okay, it isn't immediately caught by the code, but we would get an instant null pointer dereference when traversing the cell map, probably. And this is indeed true, and it's a bit of a problem for exploitation, but there is one thing that is saving us in this case, and that is the small dir optimization. Because with the normal logic, the kernel would have to allocate the full top-level directory, which has 8 kilobytes of data, even for very tiny Hives. This is not very optimal. So what they did, I think maybe even in the original implementation of the registry is that if you have a Hive that is small, smaller than 2 megabytes, which means that it fits into a single directory entry, instead of allocating the full 8 kilobytes from the kernel pools, the kernel just uses a fake one-entry array that is placed in line of the Hive security descriptor structure, which is very interesting. And suddenly that means that for small Hives, there is actually some non-zero memory at out-of-bounds cell indexes inside of the cell map. So this is how it looks. So the cell map is defined by the dual structure, and here the two fields that are important are map at offset 8, which basically has a pointer to the cell map, and then at offset 10 we have the small dir, which is this fake single entry directory array. So for a small Hive, basically what happens is that map points at the address of the small dir. Otherwise, it points to some other external allocation. And if everything is going fine and there is no memory corruption, then the directory index part of every cell index will be just 0, so we will always be referencing small dir as the first part of the cell walk. But if we can control the cell index and set it to whatever we want, of course, we can set it to bigger values and the reference other data that follows the small dir object in the structure. So this is very, very cool. And it means that we can basically perform a controlled two-level pointer to reference. So we can access one of the 1024 pointers directly following small dir. From there, we can again reference one of the 512 pointers relative to that address, and then we can add any 12-bit number and have all of that returned as the pointer to the cell by HVP get cell paged. And the structure layout in all of this is shown here. So we have this huge structure called CM Hive, which is the kernel overall descriptor of the Hive that is allocated from the kernel pool. At the beginning of this structure, we have the H Hive structure, and at the end of the H Hive structure, we have the dual structure, which has the small dir object. And the important part here is that the small dir is placed roughly in one quarter of the whole CM Hive structure. So if we can access pointers that are after small dir, then it's actually accessing pointers that are part of the H Hive and CM Hive structure, so they always have the same predefined meaning because they are part of the same structure, which also is very helpful for exploitation. So the question is now, okay, we can traverse some pointers relative to CM Hive. Where should we point a fake cell index to have any kind of interesting result? And one idea that I had initially was to take the CM Hive structure, find a pointer to a KCB object inside of it, and KCBs have another pointer that point back into the CM Hive structure. So we could do this traversal from CM Hive to KCB back to CM Hive and have the cell index point basically at the beginning or somewhere inside of the CM Hive structure in the kernel pools. And then we could, of course, add any offset up to 1000 to have the pointers point to a specific field in the structure. So here's a small visualization of that. In this case, let's assume that we choose the directory index of 251 to reach the root KCB member. From there, we use table index 1 to, again, use the key Hive pointer that points back to the CM Hive structure. Then we can add the optional offset, and this part of the structure is what is then visible as the value as the data of the value that we are crafting in the Hive. So putting all of these numbers together, we get the special index of 9F61000. And you can, for example, go in Windback and verify by using the bangrec extension to see what it translates to. And you can see that in the first parameter, we specify the address of the CM Hive structure, and in the second parameter, this magical special index. And we can see that that is actually translated back to the same address of the CM Hive. So it works as intended. So this is already great, right? Because this gives us basic access to this kernel pool structure. And there are probably many ways already from this point to escalate privileges. And for example, if you look at the beginning of the structure, you will see that at the beginning of H Hive, you have several function pointers, which looks very convenient. And this is how it looks if you actually pull off this attack and you create this kernel data value and open it in registry editor. You can see that it actually works, and you have the kernel pointers at offset 8, 10, 18, and so on. These are the function pointers from NTOS kernel. So normally it would be great if we have kernel pointers that we can read and write. Corrupting them would be very tempting, but it's 2024, so things are not as easy as they used to be. First of all, we have kernel control flow guard. And second of all, in Windows 11, it actually turns out that the calls to these function pointers are devirtualized, and they are actually not used, and the functions that they point to are called directly. So it doesn't really help us that much. But it's still, even having the access to these pointers is already great as a KSLR bypass. So what else can we do in this case? Let's go back to our grand dream of having arbitrary read and write. We know that we have full access to the CM Hive structure. So one idea for abusing it that I had would be to create two fake values, one called kernel address and one called kernel data. And so the first one would have a data backing buffer cell index pointing at some unused part of the CM Hive. And the second one would have a cell index that would basically be pointing through the same part of the structure and treating this part as the last level of the cell map. So it would be used as part of the cell walk. So in this case, if we manage to pull something like that off, we could just write some address into the value kernel address, and then immediately the data from that virtual address would be automatically reflected in the kernel data value. And as you can guess, it is possible to do something like this. And here you can see a pair of two indexes that are an example of how to achieve it. So another visualization of this is as follows. So for the kernel address, we again go through the root KCB pointer, through the key hive pointer, and then we set an offset of F14, which points to some unused part of the structure in my experimentation, and we write some address like 414141 to that place. And then for kernel data, what we do is that we use the directory index of 121, which points at some pointer that points to itself. So it's kind of a knob in this sense. And then from there, we choose a table index of 82 in order to have it point into the address that we wrote. And that basically means that that cell index then translates to the virtual address of 41414141 that we have chosen. So great, mission accomplished. With this primitive, we have basically a direct window into the entire kernel address space. And all we need to do at this point is to use the reg set value function to operate on these values, read from them, and write from them to perform a data-only attack and do something interesting. And all that's left to implement is the actual LPE logic. So that brings us to the end game of the exploit and actually compromising the system. When I devised this plan, I thought it was bulletproof and great. Nothing can go wrong. Everything works smoothly. So I was very confident in myself, but I decided to still just write the exploit as a formality to show that it works as it should. And of course, if you are too confident, what happens is you get a blue screen of that out of nowhere that you cannot explain in any meaningful way. Where is it coming from? So of course, I immediately checked the stack trace of the crash, and it turns out that the crash was caused by a backcheckx direct call that was made by the HVP release cell paged function, which previously I basically discarded as not doing anything interesting. It's just supposed to release the cell. How could it break our exploit? And then when I look at the function, it's basically this. All this function does is that it checks the cell index if it's within the bounds of the hive or not. And if it's out of bounds, then it just backchecks the system, which is not great news. It breaks the whole exploit quite badly. So as a quick recap, we had these three stages of, for example, setting the data of a value or doing some other operation on a cell index. So first of all, we translate the cell index into the pointer. In our case, it works correctly, as I mentioned. It doesn't crash and just returns an arbitrary pointer. Then this part is also fine. It just copies the memory where it should. And suddenly, the third step, for some reason, crashes. I cannot explain why it behaves like that or why the check is there. So let's think about a little bit of the cell release. I did a little bit of research to see exactly what it was used in the past, and it was kind of used on and off in Windows. So in Windows XP up to Windows 7, it was used actually to do some kind of bookkeeping and debug checks on the cell index that was freed at this point. Then it didn't exist at all in Windows 8, and in Windows 10 and 11, the only thing that it does is that it performs this annoying bounce check that we really don't like. And of course, it's kind of counterintuitive that this check is performed only after actually using the cell index. It doesn't really make much sense, but it still breaks the exploit, so it is kind of effective. And of course, if we cannot access out-of-bounds indexes, then the whole technique goes to waste. So I was scratching my head, and as a last-ditch effort, I basically started to think or to investigate what is the value that is being used in this bounce check. And if you look closely, this value is read from the CM Hive structure. It resides in the CM Hive object, and a moment earlier we get one write to a controlled cell index before we get this crash. So that kind of sounds like a CTF challenge to me. Basically, you get one arbitrary write, and then immediately after something happens and you crash, and you cannot actually exploit the bug. Very CTF-like. Yeah, you can guess probably what the idea is, right? Maybe we could find an out-of-bounds cell index that points exactly at the length member that is later used for the sanitization, overwrite with some huge value like FFFFFFF, and immediately after performing the memcopy, when the HVP release cell page function is called, it won't crash anymore because the value has just been overwritten. So here is an example of this, how it could work. So we would go again through the root KCB pointer, through the key hive pointer, and then set an offset of 38C and overwrite the length. And it works, it turns out. It's by pure luck, we actually get to overwrite the value that is used in the sanity check just probably nanoseconds before it is used for sanitization and causes a crash. And because of the fact that the length value is stored in the CM Hive structure, it's basically long-lived, so it's enough for us to corrupt it once, and then we can use out-of-bounds cell indexes for the rest of our exploit without any problems and not getting any crashes. So here is the final outcome of all of this. We get what we wanted, which is a key that has two values, and you can see that in the kernel address here, I have specified the base address of the NTOS kernel image, and then we open the kernel data value, and inside of it, you can actually see the PE headers of the kernel image. So it works as intended. And then having this primitive, there will be a demo also. So elevating privileges, of course, with this is super simple. If we have this arbitrary read and write, we can just iterate over the list of processes in the system, find our own process, find the system process, and steal the token of the system process to get admin privileges without executing any kernel code of our own. So now is the time for the demo. We have a virtual machine of Windows 11 here. We log in as a normal user. It's visible, right? Yeah. Yeah. So let's hope that it all works. We have to specify a path. Something like this. Okay. So something happened. A shell was spawned, and some messages here. So let's go to registry editor and see it live, how it works. So we have this special key, and we can actually see it all live. We have the base address of the kernel, and we have the data here that is directly mapped. So we have this direct window into the kernel address space. You can see the headers here, and what else? We can go to the PE structure of the process, put it in the kernel address, refresh, and we can see that we get the kernel data here. Yeah, I don't know what I'm looking for. Yeah. Oh, here you have the cmd.exe. So you can see that it's the PE process structure. That's cool. And then So then we generated this becomeadmin.reg file that we can use to finish the exploit. First of all, you can see what inside. So inside, we just have a write to this magic key. We write to the kernel address, the address of the token of the CMD exe process. And in the kernel data, we write the security token of the system process. So we double click on this, and it says, adding information can unintentionally change or delete file. Yeah, the system doesn't know how badly we're abusing the registry. So we just click yes, we are risking it, and OK, it was successfully applied, and then we get the system. So that was basically my talk in terms of what's next for the registry research. First of all, from the defensive side, I think there is a lot of room for mitigations and structural improvements. The first and foremost, what I would suggest is to harden the cell index translation code so that the technique specifically that I used would be killed. And it's as simple as basically moving the one if from the release function to the get function. So it's a pretty simple fix that would kill it entirely. Then we could also probably mitigate the third idea with the linear overflows between our own Hive and some other trusted data by actually separating the Hive mappings from each other and from the rest of the kernel pools, at least so linear buffer overflows cannot be used to cross the security boundary. And another idea, for example, would be to introduce integer overflow checks in the security descriptor reference counting. So I provided this and some other recommendations to Microsoft. Some work has already been done, especially on the integer overflows checks, and I'm looking forward for more of it to be introduced as well. As I told you at the beginning, I did a little bit of binary fuzzing, but it was very simple, and actually spending more time on the fuzzer and correctly implementing all of the parts of the fuzzer, such as the mutator, the harness, and the bug detection could still yield some interesting results that are separate from the bugs that I found through manual auditing. And of course, in the future, it's worth keeping an eye on any new registry features that get added to the registry. I have tried to audit all of the code that exists right now, but I'm curious to see if there is any new code in the future. And personal takeaways, first of all, I think it shows that long analysis pays off, and you can actually, by spending the time to understand very deeply how something works, you can find some very cool bugs that are deep and cannot be fuzzed out easily and have some very interesting primitives. Of course, the registry is a fascinating research target with a lot of depth. I enjoyed this research a lot. Weird machines, custom allocators, and other constructs that are escaping the realm of the traditional exploit mitigations continue to exist, which is kind of interesting that you have all of these mitigations in the kernel, but all it takes is still one bug and you get arbitrary read and write. And finally, there are insights to be gained from writing exploits, even when working on the defensive side, or maybe especially because you never know what problems you are going to encounter, and it's a very interesting exercise to see which mitigations are effective and what other mitigations could be introduced to actually prevent real-world exploit in the future. So with that, thank you, and maybe I can answer some questions. I think there are microphones in 3 places. Yeah, so feel free to use them.
Yeah, hello. Thank you for your talk. Very nice. My question is if you developed a custom fuzzer completely, or if you use the available frameworks or tools.
So for the fuzzer part, 2 years ago, I was developing my own infrastructure for code coverage-based fuzzer that was based on the Box emulator that was used for collecting code coverage and doing the communication with the guest system and stuff like that. So that was a side project that I will probably come back to, but it was all custom. And there were no registry-specific parts. So the registry fuzzing that I did was basically just bit flipping, a very simple harness that was just enumerating all the subkeys and all the values. and looking for a kernel crash. But the problem with the registry is that each part of the fuzzer that normally you have would have to be very specifically tailored to the registry, because first of all, the hive structure has a structure that is not really well suited for flipping bits. You would have to actually introduce some more meaningful mutations there. Then you would also have to have a very good harness that actually calls all of the system calls that you can perform on the registry keys, which is kind of hard to do. And finally, even when you get some kind of memory corruption inside of the hive mapping, in most cases, you don't get a blue screen of death. You get some inconsistency inside of the hive mapping that can be later maybe used for some kind of better memory corruption, but you don't see a crash. So you would also have to have some very good detection of this inconsistency in the hive mapping so it would take a lot of work to have something good for the registry, I think.
Yeah, thank you.
Thanks.
Amazing talk. Can I ask, did you find any race conditions in the registry?
Yes, I found one or two, not that many. First of all, because it's a little bit harder, I guess, to find race conditions by just analyzing the locking mechanism. So I spent a few weeks on that part, and I found some bugs that were caused, for example, in the registry virtualization. They would always assume that the key that you redirect the operation to is in a specific key hive, and they would lock this specific key hive, but you actually could point a key to some other hive. So they would lock the wrong hive, and that would mean that you can have a race condition inside of another hive. So yeah, one or two bugs like that, but that's a little bit of unexplored area, I would say, that you can look into, especially if you have some good ideas of how to actually detect these kind of race conditions.
Thank you so much.
Thanks.
Hey, thanks for the great talk. So I have a question, because if you wouldn't be able to hit this length and like bypass the check later on, could you maybe use like a race condition and do the same hijacking or exploitation from two different processes, and like maybe bypass the check later on? Like maybe there is some primitive for that, I don't know.
Yeah, so the biggest problem with that is that the window for this race condition would be super, super small, because the release function is called almost immediately, so we have maybe a few instructions in between. And also, in general, when I looked at the locking of the registry, it was pretty robust, and I think without another locking bug or some kind of race condition, actually the normal locking of the registry would prevent you from
so you're saying that like two processes cannot do this action in parallel, like this setting of values?
Yeah, probably. I would have to think a little bit more about it, but I think it wouldn't be easily possible. I mean, it's kind of hard to say, because in the registry you have so many locking mechanisms. So for some operations, the kernel basically has a global lock for the registry, and when you perform some operations, the whole registry is locked at the time. But they also have some optimization, and in some cases they don't lock the whole registry, but only specific keys that you are operating on. So it would be really a matter of finding the right set of locks that are being held, so you can at the same time modify the cell index that is checked. And I'm also not sure if they don't copy the cell index somewhere on the kernel stack or somewhere, which would even prevent you from overwriting it at the same time. So I think it's probably quite unrealistic.
Yeah.
And I think if they had the check in the right place, probably this technique would be just dead completely.
Okay, thanks.
Okay, so thank you again.